This week we're going to talk about a little bit more of complex topics in molecular bonding and structure. And the first thing we need to talk about is something called the formal charge. The formal charge is the hypothetical, that's an important term, it's a hypothetical charge that a situation would have if we would distribute the electrons in the bonds evenly between the atoms. It's hypothetical because many times those electrons are not distributed evenly. The way you calculate a formal charge is as follows, and you calculate the formal charge on each atom. The formal charge is equal to the number of valence shell electrons minus the number of lone pairs minus 1/2 of the number of bonding electrons. And the sum of the formal charge of the entire molecule, if it's a compound, will equal 0, and it equals the charge of the ion if it's a polyatomic ion. So let's look at this example of iodine tetrachloride. So iodine has 7 valence electrons minus, there are 2 lone pairs, so minus 4, minus 1/2 of the 4 times 2 bonding electrons, so 1/2 of 8. So the total formal charge of iodine is minus 1. Chlorine has 7 valence electrons, 6 lone pairs, and each chlorine has 1 pair bonded. So if you take and add all that up, you get 0. So the formal charge for this entire molecule is minus 1 plus 4 times 0, or minus 1, which is the charge of this polyatomic ion. Let's look at this. Carbon, and I'm going to show you visually as well, but carbon has 4 valence electrons, minus 2 for the lone pair, and there are then 3 bonds. So that's 3 times 2, and that's 1/2 of that. So carbon would be 4 minus 2 minus 1/2 of 6, or 3. So it would be a minus 1. Oxygen, on the other hand, is 6 minus 2 minus 1/2 of 6, which is 3. So it's plus 1. Minus 1 plus 1 equals 0, and this is a compound, so it should equal 0. And here it is written down. So you can look at this and see carbon has 4 valence electrons minus the 2 lone pairs minus 1/2 times 3 for the triple bond times 2 for a pair of electrons per bond. So the total is minus 1. Oxygen is 6 minus 2 for the lone pair minus 1/2 times 3 times 2, or plus 1. And then the total is minus 1 plus 1, or 0, which is what you find when you have a compound. The molecular structure will arrange itself in such a way as to take into account these formal charges. A structure where all the formal charges are 0 is preferred. If that is not attainable, then the structure with the smallest formal charges is preferred. If it is preferred to have adjacent structures be 0 or opposite charges. And then lastly, all else being equal, it's preferred to have a negative formal charge associated with an atom with a high electronegativity. So here are some examples. You have 3 different ways of writing carbon dioxide, and the one on the left here would be the preferred because all the formal charges are 0. The one in the middle would be next in line because it has a lower or smaller formal charge, and the one on the right is the least preferred because it has higher formal charges and because you have a plus and a minus together. So here's another example. You have 3 different ones. In your mind, select the one you think would be the most likely molecular structure for this compound. Or excuse me, in this case it's an ion. The first arrangement, or the arrangement on the left, is the preferred, since it has the lowest atoms with the non-zero formal charge. You only have one atom at -1, whereas the other two has two atoms, or all three atoms have a non-zero formal charge. Which of these two structures is preferred? Stop the video at this point, figure out the formal charge given these two structures, and decide in your mind, on paper, which of these two would be the preferred structure, and then restart the video and I'll give you the answer. First, you have to determine the formal charge on the two structures, and here it is. And if you need to go through the calculation again, we can do that in class. You'll notice that the one with the more zero formal charges is the one on the left, so hopefully you pick the one on the left. This is preferred because it has the lower formal charges. There will be something on a quiz where I give you examples and ask you to circle the one that's the preferred, and you need to be able to show how you calculated the formal charge. Now let's switch here and talk about resonance. Resonance occurs when you can put together two or more structures with the same arrangement of atoms. And the actual structure is generally what is known as a resonant average, or an average between the two choices. So for example, here is an example where you could have the double bond on the right or the double bond on the left. This is the nitrite ion. And the truth is that both of these exist. It exists as the structure on the left half of the time, and the structure on the right the other half of the time. And that is generally written this way. What you do is you put dashed lines to represent half the time the double bond is on the right and half the time the double bond is on the left. And you also generally write a little double arrowhead to show that structure. Now if you use a dashed line, you generally don't necessarily need the arrowhead. What the arrowhead is frequently used for is if you use a solid line to represent a double bond and a single on the other atom, and then you switch it on the other side. So these two are known as the resonance forms. It's the possible individual structures. Actually, these are the two resonance forms right here. And the resonant hybrid is what's shown in this slide, which is the average actual molecular structure. Now here's an example where there's three resonant forms. You can see that the double bond moves from one oxygen to another oxygen to another oxygen. So you have three resonant forms. And interestingly, experiments show that all three of these bonds are exactly the same length. Now that would not be true if any particular oxygen were preferred for the double bond. What this tells you is that the double bond oscillates between the various oxygen possibilities in nature. Now when we talk about bond strength or bond energy, also known as bond dissociation energy, is the energy required to break a specific covalent bond in 1 mole of a gaseous molecule. So here we have methane on the left here, and we have broken the 4 carbon-hydrogen bonds to form carbon as a gas and 4 hydrogen atoms as a gas. And the energy required to do that is 1660 kilojoules. So each bond would be 1/4 of that number. So the bond association energy for each of these bonds would be that number divided by 4, or 415. The total here, the sum of all these bond energies, actually equals the enthalpy of formation, which we talked about a few weeks ago. Now, if I give you the bond energy for each of these bonds, you can calculate from that bond energy the approximate enthalpy of change. So you can take the bond energy, and how you do that is as follows. You sum the bond energy that's needed to break all the bonds between the carbon and the oxygen and the hydrogens, and subtract from that the energy that is used to form the bonds between the carbons and the oxygens and the hydrogen in the products. And the difference between those two sums is equal to the change in enthalpy. And it can be shown here. So the bond energy between C and O, you're actually breaking 3 bonds there, plus 2 times the bond energy between the 2 hydrogens. You sum that together and then subtract the sum of the bond energy between carbon and hydrogen, between carbon and oxygen, and between oxygen and hydrogen. And you have to take 3 times the carbon and hydrogen because there's 3 carbon-hydrogen bonds. And the numbers, which I got from the book, if you put the numbers in, you get a delta enthalpy change of minus 107 kilojoules.